Hey there everybody, this video just picks up right where the last one left off. And where did we leave off? We left off by pointing out that if you wanted to sketch the graph of a function, and we were pretending we didn't know what the graph of this function looked like, you can sketch that guy's graph if you know two things. If you know a single point on its graph, and you know slope information. So the slope data plus a single point allows you to sketch a graph of this guy by sort of stitching together tangent lines. Okay, so of course in this example that's kind of silly because we know precisely what this guy's graph looked like. That's not an issue. However, let's move on to the differential equation portion, the thing we care about. Suppose I ask you to solve this initial value problem, and when I say solve, what I really mean is, can you sketch me a graph of y? Can you tell me what y looks like? Well, now we don't know what y looks like. We don't just have a formula for it, right? But what do we know? We know a point on the graph of y. That's just handed to us as part of the initial value problem. We know that y goes through the point 0, 1. And what else do we have? We have slope data. That's what that differential equation is. It's a formula for slopes. Therefore, the process outlined on the previous slides from the previous video can just be applied here in exactly the same way to sketch a graph of y. So if you want to sketch a graph of y here, the first thing you do, as we did before, was pick your step size. The smaller the step size, the more accurate your sketch. Let me just pick a step size of 1/2 here. Well, just like before, this formula from Calc 1 still holds. All it says is the change in y is the slope times the change in t. That doesn't change. So if we're at a point 0, 1, and we want to ask ourselves, well, if I move to the right a little bit, if I move to the right by, say, 1/2 second in time, by how much will y change? You can, again, just use this formula. So dy is y prime dt. Well, what is y prime? It is this formula, which now involves both y's and t's, but that is fine, because if we are at this point here, we have a t value of 0, we have a y value of 1, so we can just plug those values directly in. So here's my t of 0, right? T times y, here's t times y, plus y squared minus 1, times my step size, right? Y prime times dt. So I get 0 plus 1 minus 1 is a 0. 0 times 1/2 is 0. So what does that mean? If we take 1/2 a step to the right, y, we estimate, doesn't change. So if y used to be 1, then y will still be 1. Right? The change was 0. So a 1/2 step to the right meant no step vertically. Neither a step down nor a step up. Okay, well, just like before, once you have a new point, you can just completely iterate this process. It's completely mechanical. So now if we're at 0.51, now we have a t value of 1/2, a y value of 1. So if we want to think about taking another 1/2 step to the right, so that now we're at time 1, how much does y change? Same formula, dy equals y prime dt. Well, now y prime, the numbers you plug in are different because we have a new point. Right, now we plug in the point t equals 1/2 and y equals 1. So here's t equals 1/2, y equals 1, y equals 1, and this minus 1 is always there, right? Minus 1 right there, times my step size. Okay, so what is this? This is a 1/2 plus 1 minus 1 times 1/2 gives me 1/4. So what does that mean? When I take my 1/2 step to the right so that the t value is now 1, I have increased y by 1/4. So if y used to be 1, well, if y used to be 1, y is now 1 1/4, and so on. I have one more move here. You can just keep doing this off to infinity if you feel like, you know. So now if t is 1 and y is 1.25, the change in y is the slope times the change in t. Now I plug in a t value of 1, a y value of 1.25, y value of 1.25. So now square that, minus 1 times 1/2. If you plug this into your calculator, you get roughly 0.9. So what does that mean? When I move from t equals 1 to t equals 1.5, that half step in time, y increases by roughly 0.9. So if it used to be 1.25, now it's this number here. Okay, so that's how Euler's method works. I could just slowly build a graph of y off of that differential equation and off of that initial value. I should say real quick, by the way, as we pointed out last time, the smaller the step size, the better your graph. Also, the closer you are to your original point, the better the graph. We would expect whatever errors there are to sort of cumulatively accrue as we do this. So if you end up at time a billion, right, even using a small step size at time a billion, this y value you're estimating might be far from the actual y value. Okay, so let me just move on to an exercise here. So use a step size, again, of time t equal a half. The step size, I'm just choosing to be relatively nice. You can use whatever step size you want in general to estimate y of 2. Here is the differential equation. Here is the start point. So pause the video and see if you can estimate what y of 2 is. Okay, assuming you're back, let me just show you the solution. It's about 17.59. It should have taken you 4 steps to do this, moving from time 0 to time a half, moving from time a half to time 1, from 1 to 1.5, and then finally from 1.5 to time 2. That would let you estimate. So in other words, you're doing this process here, but you take it 1 step farther than I did. You move to t equals 2, and once you move to t equals 2, you can read off what the y value is. And that y value should have been 17.59. Okay, before moving on to systems of DEs and closing out this section, let me just show you real quick this GeoGebra Euler's method little visual here. It's pretty nice. The link to this is on Moodle. So in this calculator, right here you type, so it says f of xy. This is the derivative information right here. So that's where you type the derivative stuff. And I'm using this DE right here, ty plus y squared minus 1. In this little applet here, you have to rewrite t's as x's. That's why there's an x right there. You tell it the start point. So when t is 0, y is 1, and you choose your step size. This blue graph is the resulting Euler's method graph. Okay, so here are our points. So what do we had like a, what was our step size? It was t equals a half. So now, let me decrease the step size to t equals a half. They use an h here for step size. Okay, so these 4 points here that they've built are our same our 3 points. We built 3 points, right? So we went from 0, 1, which is right here, to what? A half 1, that's that point right there. And then from a half 1, we moved to 1, 1.25, that's that point right there, and so on. Now, the really nice thing about this Euler's method calculator is that if GeoGebra is capable of solving this differential equation, so this differential equation, then GeoGebra will solve it and it will plot the actual solution here. This purple curve is the actual solution. So the reason I like this little applet here is you can see how good the Euler's method is given a step size. So a step size of a half, I mean, it's pretty good. You know, there's obviously a gap between purple and blue, but I don't know, the blue is tracking with the purple. And so when you play with step sizes, you can sort of try to see, you can actually see the smaller step size giving you a better graph. So if I do 0.2, look at that. So a step size of 0.2 is way better. 0.1, and if you do something like 0.01, then the purple and the blue are like identical, you know. And certainly if you do, I'm not sure how far I can push this, but 0.001, yeah, it wouldn't let me, too small. I mean, at some point it takes so much computational power, right? But I'll do 0.008 to see if it lets me do that. It does. So 0.08, see, so many little points, right? So many little tangent lines. I'm sticking so close to the original curve that to the naked eye, the blue and the purple are basically the same. So anyway, this link is on Moodle. You can play around with this if you want. It's pretty fun to play around with, given a DE and given a step size. You can watch that step size sort of zero in on the curve you care about. And again, not to belabor the point, but if you make the step size big, like 2 or something, I mean, it's not great. Right? The larger the step size, the worse the approximation is. It's still, by the way, tracking, right? It's still tracking with the purple, but not great. Okay, so let me conclude this by now talking about systems of differential equations. By the way, the reason that the sections are 2.7 and 8.5, 2.7 covers what I just did. 8.5 covers the systems part. And the systems part, again, is what we care about because we're going to be using Euler's method on systems of DEs in the epidemic models section. So let me just quickly walk you through that. So suppose you have a system of DEs that looks like this. So x and y are both functions of time. So to solve this initial value problem means to sort of simultaneously find x of t and y of t, right? So simultaneously drawing graphs of x of t and y of t. So what I'm going to show you here in a second, it looks kind of intimidating at first, at least I think it is. However, it's no different in principle from what we just did. So whether you're dealing with a single DE or a system of DEs, Euler's method just kind of goes on autopilot. It just uses the slope data to estimate how much the function is changing, and then just adjust the second coordinate accordingly. Okay, so let's just use a time step of size 1 to make this thing nice. So notice, since x of 0 is 2, that means that at time 0, the graph of x is at 2. So it's kind of obnoxious here, as always, to have x being a dependent variable, but what are you going to do? That's the way things are in like chapter 9, for example. So x and y are dependent depending on t. So this is an x coordinate here. Sorry, this 2. Why won't it let me? Whatever. So that 2 is an x coordinate. That 0 is a t coordinate. And this 0 is also a t coordinate, but that's a y coordinate, right? Anyway, so if you're at the point 0, 2 on the graph of x, then this formula still holds. If you want to estimate the change in x, you take the slope information for x and multiply it by your step size, your change in time. Okay, so this formula here, that's the slope information for x. So if time is 0, and it is at this point, right? When time is 0, x is 2. When time is 0, y is 1. Right, so notice this formula involves 3 variables, t, x, and y. But if you know a t value, then you know x and y also, because they're functions of time. So when t is 0, I put a 0 there, right? Here's x at that time, here's y at that time. Then I have a minus 1, and then times my step size, and I get 1. So if I take a step to the right of size 1 in time, x, that variable changes by 1. So if it used to be at 2, now it's at 3. So that's how you can get the next point on the graph of x. Well, what about the next point on the graph of y? We know y starts at 0, 1. So now, to estimate how y changes, use this formula. Change in y is slope data for y times the change in t. The step size for t is still 1. Notice y prime, here is its slope information. So if time is 0 right now, and it is, right? Time is 0 right there. At 0, y is 1, so 1 goes right there. At 0, x is 2. So I put a 2 right there, and I get a 4. So if y used to be here at 0, 1, it goes up by 4. So now the new point is time of 1 and y value 5. And now you just iterate that. So 1, 3 is a point on the graph of x. So if you want the next point, right, again, this formula still holds. So now I have to think about at time 1, time is 1. So 1 goes right there, right? At time 1, x is 3. At time 1, what is y? At time 1, we just said that y is 5. That's what we estimated. So when you use this method on a system, you have to do x and y simultaneously. You have to take... You can't sort of do x by itself, is all I'm saying, right? Because the slope data for x depends on what the value of y is. There's a y there, right? And similarly for y, its slope data depends on x. There's an x there. So you have to do this simultaneously. Anyway, that's why there's a 5 right there, times my time step of 1. This is, whoops. No, that's right. Okay, yeah. 15 plus 1 minus 1, 15. So anyway, x increases by 15. So I go from 3 to 18. 1, 5 was a point on the graph of y. Change of y is y prime times dt. And again, this x, the reason I put a 3 there is because this is all happening at time 1. There's a time 1 right there, right? At time 1, y is 5. At time 1, x is 3. That's what we said, right? At time 1, x is 3, we estimate. This number is 14. So y increases by 14, so my next point is 219. And so on. You can just keep this going if you want to. Just making sure you do both variables simultaneously as you go. So that's how you can solve systems, a first order system using Euler's method. So finally here, I want you to do this exercise. Use a step size of t equals a third. So take a third second steps to the right to estimate these two values. So what does that mean? You're going to go from t equals 0 where you know things, to t equals a third, to t equals 2/3, to t equals 1, and figure out what these values are, or what you estimate them to be. So pause the video and I'll see you back in a second in my time. All right, so just to show you how the process gets going, so this is just like the last slide. If we're at 0, 1 on the x graph, right, that's where we start on the x graph, change in x, slope times time. So here's x at time 0, there's y at time 0, times 0, plus y at time 0, times my step size. Always have to multiply by step size, and I get 4/3. So I take a third second step to the right, so I go from 0 to a third, and I increase x by 4/3 to get 7/3. From 0 to, change in y is y prime times dt, so now y at time 0 is 2, so I have 2 squared over 2, gives me my 2 right there. Time is 0, so 0 times x, doesn't matter what x is right now, right? But x would be 1. This is 0 times 1. Minus 1 times my step size is a third. So I increase time by a third. I increase y also by a third. So I go from 2 to 7/3. So anyway, after a third of a second, we actually estimate that x and y are in the same place. Okay, so if you do this 2 more times, why is it doing that to me? Anyway, do it 2 more times, you'll eventually get that x of 1 is approximately something like 11.6. I started rounding, just getting decimals and rounding, so yours might be a little off of that. And y of 1 I got to be 5.61. Okay, so in the next video we'll start the epidemic models unit, and we're not going to get to the Python script in the next video. However, once we do get to the Python script, I want you to think of this. This is all that's happening behind sort of like the seeming black box that is the Python script.